No, you haven't listened to the lecture yet, have you?
No.
Because at the end of one of those lectures, I said, listen, folks, chapter 28, the last chapter, we're not going to do 29.
At all?
At all. And I said, and I'm not cheating you, the face-to-face classes don't do 29. I was going to try just because listening to the lectures is on your time, but I realized that you guys are running out of time. So I said, you know what, I'm not going to do 29. Pretty cool chapter. It's embryology, development. So it goes through after the fertilization. So in chapter 28, we stop at fertilization, right? Then in 29, we go into how the placenta forms and the 4 layers of the chorion, amnion, and all those 4 layers. And all right, so this picture's on the test. So obviously, you need to go look at it if you don't know the 2 joules and stuff like that. And you know the difference between secretion and reabsorption. All right. Okay. Now, let me make sure that's really the only picture. That's the only picture. Now, let me go through the test from beginning to end. You have to know how the renal system regulates blood volume and blood pressure. What that is erythropoietin, and it's the renin-angiotensin-aldosterone system. So erythropoietin in the renin-angiotensin-aldosterone system. Now I hope by this time you guys realize that you have to be a master at both of those things I just mentioned. You can't just say, oh, I know erythropoietin. Well, where does it go? If you don't know it goes to the bone marrow, then you don't know everything about erythropoietin. If you don't know it turns on erythropoiesis, which is red blood cell production, you don't know about it. The renin-angiotensin-aldosterone system, you have to know how renin converts angiotensin into angiotensin 1, how ACE converts it to 2, what everything that 2 does. Therefore, you have to know what ADH does and what aldosterone does. The whole system. Okay, so I think you guys know me by now. When I say that, I make it sound real simple, but you have to go back and be a master at that material. Because I ask it in different ways. Not tricky ways, but different ways. And make sure you know the juxtaglomerular apparatus. What starts the whole renin-angiotensin-aldosterone system is the JGA. Make sure you know the JGA.
So would you review that briefly? So there's 3 parts that make up the JGA. The macula densa, mesangial cells, and
Juxtaglomerular cells.
And so the last one, they're part of they're smooth muscle cells, right?
Which ones?
The juxtaglomerular. So which ones secrete the renin? Are they both? The macula densa?
JG cells definitely do. We think mesangial cells probably do. Macula densa cells tell the mesangial cells and JG cells to secrete. I think your book says, and I remember saying in the lecture, we don't know everything about the mesangial cells and everything they do, but we do know they have gap junctions that connect the macula densa to the JG cells. All right. Make sure you know about filtration in the glomerulus. That means from the fenestrated endothelium, the fenestrated capillaries, to the basement membrane, which we call the dense layer, which is negatively charged, to the filtration slits of the podocytes. Make sure you know the filtration membrane. I would remember, I don't know if you need to memorize the exact measurements, but knowing approximate measurements would help you. The fenestra are about 90 nanometers diameter, and the filtration slits are about 9 nanometers diameter. And the dense layer is negatively charged, so it repels anything that's negatively charged. So basically, anything that's positively charged that's less than 9 nanometers gets through. Anything that's neutral that's less than 9 nanometers gets through. But anything that's negatively charged or bigger than 9 nanometers doesn't make it. Okay? So I have a question for you. Does anything make it into the filtrate that our body actually needs? Yeah, a whole bunch of things, and we reabsorb it. Okay, good. All right. Make sure you know what renal threshold means and tubular maximum. Make sure you know the difference between renal threshold and tubular maximum. Who wants that explained right now? Okay, renal threshold is a blood value. The renal threshold for glucose is 180 milligrams per deciliter of glucose in the blood. So why do I call it a renal threshold? It's because it's that blood value, that value and above, where I start spilling glucose into the urine. That means I can't reabsorb it anymore. So why can't I reabsorb a renal threshold of 180 milligrams per deciliter of glucose in my blood? Because that much blood glucose gives me a filtrate that overcomes my tubular maximum. What does that mean, tubular maximum? My glucose transporter is saturated. I can't transport anymore. I've hit my tubular maximum. So that means I can't reabsorb it and it stays in my urine. Any questions now about renal threshold and tubular maximum? Renal threshold is a blood value of that analyte, like glucose or amino acids or whatever. Whereas the tubular maximum is a saturated transport molecule in my tubules, my renal tubules.
So they're both referring to the same event.
They are, but one is a saturated transport protein and one is a blood value. But they are talking about the same event, spilling off into the urine. Yep. Yep. Yeah, they're linked. They're similar, but there's a difference. All right. Make sure you know about how much renal filtrate we make in a day and about how much urine we make in a day. So we make about 200 liters of renal filtrate in a day, and we only urinate out 2 liters of urine a day. Therefore, we must reabsorb all the rest. All right, you have to do some math. At the glomerulus, there's some pressures, filtration pressures. There's the glomerular hydrostatic pressure pushing out, and there's 2 pressures pushing in. Well, there's one pressure pushing in, one pressure pulling in. There's the capsular hydrostatic pressure pushing in, and there's the blood colloid osmotic pressure pulling in. Any questions about that? Okay, so here's what I say. Which of the following formulas will allow you to calculate the net filtration pressure? You have to pick the formula that does it.
Do you give the numbers or do you give the names of the
In
pressures?
that case, I didn't give any numbers, but I do later.
Okay.
Let's be clear. Else you guys will think I'm being tricky. This is Bowman's capsule. Afferent, efferent, capillaries. These are my caps. My glomerulus. Alright? My glomerulus. So, I have a glomerular hydrostatic pressure pushing out. Okay? Put a number to it. I have a capsular hydrostatic pressure pushing in. I also have a blood colloid osmotic pressure. So my net filtration pressure is the outward minus the sum of the inward. All right, so one way of writing it that's one way of writing it. Is there another way of writing it? Yeah, I mean, I could just write it like this. It's the same thing. Those two are equivalent. Now I'll prove it to you. Let's say this is 55. Let's say this is 25. And let's say this is 10. All right? So my net filtration pressure equals 55 minus the sum of 25 and 10. In other words, it's 55 minus 35. Let's use this one. Net filtration pressure equals 55 minus 25, which is, what is that? 30. No, 25, 55.
It's 30.
30.
30 minus 10, 20. 20. Same number. So just make sure you see these pressures and be able to just write the formula. Obviously, there's different ways to write the formula. I don't know what I choose. All right. Then I add numbers to it. Here's what I say. Measurement of the function of a nephron reveals a glomerular hydrostatic pressure of blank millimeters of mercury. I'm not going to tell you what the number is. In the pressure in the capsular space of blank millimeters of mercury. What's the pressure in the capsular space? Up here. Blood colloid osmotic pressure or capsular hydrostatic pressure?
Capillary
What's the-
hydrostatic.
Yeah, the pressure in the capsular space. Yeah, it's capsular hydrostatic pressure. Assuming that the colloid osmotic pressure is blank, and that essentially no proteins enter the capsular space. So here's what I'm saying to you. What's responsible for this blood colloid osmotic pressure? Albumin. So I'm saying assume no albumin gets to here. It doesn't normally anyway, but it can after like excessive exercise or something. But I'm saying assume no albumin gets to here. So therefore you don't have any blood, you don't have any capsular colloid osmotic pressure. None. So no protein crosses. Assuming no protein crosses. What is the net filtration pressure in this case? So you have to do the math. You have to be able to pick a formula and then you have to be able to apply the formula. That's numbers 9 and 10. Pick a formula, hopefully the correct one. Apply the formula. Do the math. Any questions about that? Good. I asked you how you make concentrated, so small volumes of concentrated urine, and I asked you how you make large volumes of dilute urine. Now, this is not something different. It's just another way of saying it. I make small volumes of concentrated urine using ADH. I could be using aldosterone depending on what's stimulating this. It depends what stimulated it. But both ADH and aldosterone make me reabsorb water out of my filtrate and make small volumes of concentrated urine. I make large volumes of dilute urine with natriuretic peptides, diminishing the ADH secretion. All right? Make sure you know the difference between secretion and reabsorption. All right? Secretion and reabsorption. You know that picture I showed you? Not on the picture yet. I'll tell you when I get to the picture. But make sure you realize where the hormones act on that picture. Basically, ADH and aldosterone act in the distal convoluted tubules in the collecting duct. So that's where the hormones act. By the way, on that picture, the arrow should have been dotted at the distal convoluted tubules in the collecting duct. They're dotted because it's variable. It's facultative, which means the hormones affect it. All right? Make sure you know the detrusor muscle and the micturition reflex, the urination reflex. Then I have a very cool question for you about osmotic pressure. Can't tell you. The 24. The 24 is a really cool question. Then I have the picture. Let me tell you how many questions go to that picture. 8 questions go to that picture. Okay, so we're on, by the way, just in case you're wondering, we're on chapter 20. The test is on chapter 27. In case you didn't realize, chapter 26 and 27 are very closely linked. The kidney chapter and the fluid electrolyte acid base balance are very closely linked because the kidney does a lot of that for us. So to me, they're actually kind of like one chapter. There's just 2 chapters for you guys. Again, in chapter 27, you have to know about atropine and angiotensin aldosterone. You have to know about AMP and BMP. And then I go into this whole thing about respiratory acidosis and respiratory alkalosis, and metabolic acidosis and metabolic alkalosis. Here's what people miss these questions. Please remember, low pH is acidic and high pH is basic. Please don't forget that low pH is high hydrogens. Low pH is high hydrogens, acidic. High pH is low hydrogens, basic. That's why people miss these questions. And then when we go to the test, they go, oh, I forgot low pH is high hydrogens.
You said we should ask about the anion gap. Is this a good time to ask about it?
Yeah, sure.
'Cause I didn't understand that.
Oh, I'll go over it. Let me see if it's on the test. I'll tell you if it's on the test. But I'll go over it. It could help you. It can help you. So I don't have you calculate the anion gap, but it can help you. So what happens is this. If you have metabolic acidosis, well, let me just tell you what the anion gap is. The anion gap is an unmeasured anion. It's a gap. When we add all our cations should equal our anions. Our blood doesn't flow around charged. Are there charged things in my blood? You bet. There's charged things in my blood. Well, my blood is neutral. It's not like you have little bolts of electricity shooting around your body left and right in your blood flow, right? So it's just neutral. But if I add up my cations and I subtract my anions, I get a number. It should be 0, but I don't get 0. I get like 12 or 15 or 20 or what? 12. Let's say I get 12. Let me try to make this 12. 150 plus 5. This is 155. Minus 110 and 20 is 130. Let's try to make it 12. Plus 120 plus 25 is 145. That's good enough. 120 plus 25. So that's 145. That'll work. That equals 10. My anion gap is 10. I'm lacking 10 anions that are unaccounted for. All right? Now, this anion gap goes up with metabolic acidosis, especially organic acids, like lactic acid, acetoacetic acid, acetic acid, beta-hydroxybutyric acid, those ketones and things like that. Here's why this anion gap goes up with metabolic acidosis, especially the organic acids. If I add lactic acid, a bicarb is consumed by buffering it. So remember how I got this 145. So if I add a keto acid, this becomes 24. Now that's only 144. Now that's 11. It's going up. I add another lactic acid or beta-hydroxybutyric acid or keto acid, whatever. This becomes, it consumes a bicarb. Let's say this goes down to 15. I consumed 15 bicarbs buffering that organic acid. This is now 135, and this is now 20. See how my anion gap went up with these organic acids? So what happens is I have this anion gap, which is some unmeasured anions. The more unmeasured anions I have, like lactate and acetate and acetoacetate and beta-hydroxybutyrate, all of those keto acids, the more I have, the higher my anion gap goes. It tells me something in the lab. It tells me I have metabolic acidosis, usually due to organic acids. Like diabetic ketoacidosis gives me a high anion gap. Okay? Now I don't have, your test doesn't have you calculating anion gaps. I can see where that concept could help you on one of these questions. So back to the test now. You definitely have to know what respiratory acidosis is. You're not breathing very well. You're retaining CO2. It shifts that whole equation to the acids and you get respiratory acidosis. You have to know what respiratory alkalosis is. You're hyperventilating. You're blowing off CO2. You're removing it from your bloodstream, so you become alkaline.
And I had a question about that. So I think you also said that with chronic respiratory alkalosis, the bicarb would go down.
Acidosis?
Alkalosis. It didn't make sense to me. Maybe I didn't write it down.
With chronic respiratory alkalosis?
Yeah.
So you're hyperventilating constantly?
Yeah.
I'm asking.
Yeah, I guess so.
Your bicarb would not go down.
Okay, maybe I wrote it down. See, yeah, it didn't make sense. It's possible.
Wait a minute, your bicarb would go down. Why?
Why? Yeah.
Because your kidneys are going to get rid of it because you're already alkaline. See, bicarb's a base. Now your kidneys are going to urinate out this bicarb because it's a base, and it's going to try to bring you back to normal pH. Yeah, I agree with that.
So it would be decreasing, but would it be below normal then?
If you catch it, depends when you catch it. If you catch it, well, you said chronic. If you're catching it in the chronic state, yeah, it's going to be below normal. Yeah. If you catch it in the chronic state, yes. If you catch it acutely, not yet. No.
Okay.
Make sense?
Yeah.
Yeah, I agree with that statement. You didn't write it down. Remember this. If I have problems with my breathing, like I'm chronically hyperventilating or I'm chronically hypoventilating, okay? If I have problems with my breathing that way, then my kidneys are going to adjust. They'll either urinate out protons, which is the acid, or they'll urinate out bicarb, which is the base. My kidneys adjust. If I have problems with my metabolism, my breathing adjusts. I will do Kussmaul respirations to get rid of excess acids. That's hyperventilation. Or I will slow my breathing down to retain the acids, to retain the CO2. So I'll adjust, but it depends what's wrong. If I can't adjust my breathing because I have COPD or emphysema or something, then I can't adjust my breathing. My kidneys adjust. But if I can adjust my breathing, I do. All right, and likewise, you have to know metabolic acidosis and metabolic alkalosis. And that's things like these keto acids we talked about. Diabetic ketoacidosis. Metabolic alkalosis, it happens. It's not as common. It doesn't happen as common as metabolic acidosis. You could get metabolic alkalosis overdosing on Tums or Rolaids or whatever they're called. You could get metabolic alkalosis just by overdosing, taking so many Tums or Rolaids just to try to get rid of your All right, and that's the end of acid base. And then I get to the reproductive chapter. I definitely talk about interstitial cells, Leydig cells.